Good afternoon, everybody. Welcome to this webinar from Ampcontrol. My name is Phil Riley, and the presentation is called Power Transformers, Oil Diagnostics, Failures and Life Extension. There are further 2 presentations to follow this year. We hope you find the webinar useful. Its purpose is to offer you some practical guidance on working with transformers. Please use the questions box for your questions. And I'll look at these at the end of the presentation. So what I'd like to cover today is split into 2 parts: avoiding failure. I'll touch upon briefly transformer reliability, how we understand condition during operation, how we identify failure modes with a particular test called dissolved gas analysis. And then in the second part, I'll look at life extension, briefly talk about aging process of the paper, oil testing to assess the aging process. I'll touch upon briefly life extension activities. And finally, I'll finish off with some alternative fluids and their use in transformers. I'll begin with transformer reliability. I've extracted some statistics from transformer reliability surveys. The 2 surveys I looked at had representation from 93,000 transformer operating years. And here are some key points. So the failure rate is less than 1% across all voltage classes. So we know that they're reliable, but we also know that they fail occasionally. And recently I was working with a company in New South Wales, where an unexpected failure of a furnace transformer occurred. It stopped production, and this costed the company, it was costing the company $40,000 per hour. Short circuits and lightning strikes are more likely to cause unreliability than aging of the oil in the paper. So this was something else that I read from one of these surveys. And recently we worked on a 25 MVA transformer that was struck by lightning. So the winding was damaged, and we had to do a full rewind for the customer at our transformer manufacturing facility in Newcastle. In substation type transformer failures, the main locations of the failures are in the windings, in the tap changer, in the bushings. And in my next presentation, in a few months, I'll be talking more about on-load tap changers. And one of the surveys also looked at the failure rate in transformers, 220 kV and 380 kV transformers. They saw a clear link between increasing age and the failure rate of the transformer. And now one of the references, a reference for one of the surveys, is down below. So how do we understand condition of a transformer during operation? So the more information we have about condition, the more opportunities we have to intervene to avoid failures and extend life. We can do lots of different types of inspection and tests on a transformer to help us understand condition. So this diagram we're looking at was taken from a technical brochure that was published by CIGRE in 2019 called Condition Assessment of Power Transformers. You can spend a lot of time here. I'll just quickly go through it. So if we look at dissolved gas analysis, this is a test we perform on a transformer oil sample. High temperature heating or discharges of energy produce ethylene and sometimes acetylene. This can occur because of changes in the structural integrity of the core and the coil assembly and their alignment and position within the tank. And here I'm referring to this section, active part mechanical. And the only 2 outputs or actions from active part mechanical are replacement and failure. And to further understand mechanical problems, we would look to electrical test results. So for instance, sweep frequency response analysis, winding resistance. They're 2 of the tests that we can look at. Higher temperature heating can start in the oil, or it can be in the paper insulation. And heating can lead to breakdown of the paper insulation, which can reduce the life of the asset. An active part thermal relates to heating problems that degrade the paper insulation. And we can evaluate the involvement of paper in a heating fault if we see elevated levels of carbon monoxide and carbon dioxide in the dissolved gas analysis, although this assumes that large amounts of paper involved, which may not be the case if the fault is, for instance, in a paper-covered lead. We can also apply dissolved gas analysis to tap changes to help us identify problems that can be managed with an appropriate maintenance response. And on-load tap changes do fail, and it's important to understand their condition. We can measure partial discharge in the bushings, also in the main tank. And let's move down the list. Oil acidity. So the oil is an electrical insulator. It also preserves the paper insulation, which is also an electrical insulator. High levels of acid can develop for a number of reasons, including aging of the oil and breakdown of the paper by heating. Very high levels of acid can corrode metal parts in a transformer, and sludge, which comes from oxidation of the oil, can also block up the cooling fins and reduce the efficiency of the cooling system. This can lead to overheating. Acidic oil can also degrade the paper insulation directly. The consequences can be a requirement for oil treatment or premature replacement of the transformer if the paper insulation reaches end of life. Here are some very useful technical references that can directly relate to condition assessment of power transformers and tap changes filled with mineral oil, natural and synthetic esters. So you'll get a copy of this presentation. We run a NATA accredited transformer oil test facility in Newcastle in New South Wales. The company is Verico. It's an independent test organization within the Ampcontrol group. We regularly test oil samples, and the common tests that we do are listed on the left-hand side: dissolved gas analysis, oil quality testing, furan analysis to evaluate the condition of the paper insulation. So I'll talk more about these through the presentation. And my colleague from the lab is holding a transformer oil sample that was taken in a 50 ml glass syringe. So the oil in the syringe has never come into contact with the atmosphere. So we won't lose any gases from the sample, and we won't have contamination of the sample with atmospheric moisture. And from a 50 ml glass syringe, we do dissolved gas analysis and moisture testing. We think the test results are more accurate if you do use a 50 ml glass syringe, and the condition assessments are more likely to be accurate also. Let's look at dissolved gas analysis in slightly more detail. So this test, DGA, has been used to monitor transformer condition since the late 1960s. From your 50 ml glass syringe, we try and identify these faults on the left. It's important to note that more than one fault can occur at any one time, and so this complicates the analysis and also the condition assessment. These faults in red are the ones we really don't want to see. Discharges of high energy, D2, discharges of low energy, D1, high temperature heating above 700 degrees Celsius, T3, and also carbonization of the paper. So this table on the right, it's taken from a technical brochure from CIGRE, published in 2019, called Advances in DGA Interpretation. And the table outlines the severity of faults according to the location. We see that heating faults located in the paper, such as a T3 thermal fault, can be more severe to the transformer than if it's located in the oil. A D2 fault, discharges of high energy, is very severe regardless of paper involvement. A transformer failure is quite possible, and if you're fortunate enough to see the fault in time from your dissolved gas analysis results, you immediately need to retest your dissolved gas analysis and look for further condition information via electrical testing. So this is a case study from 2019. It's a 1 MVA transformer. Primary is 3.3, and it was manufactured all the way back in 1977. So we've got some test results here: dissolved gas analysis, oil quality, furan testing. Normally you take a sample once a year. These samples were taken 4 days apart, and this gives you an indication that we were concerned about the condition of the asset. And this is primarily because this acetylene appeared on the 10th of October. The results indicate high temperature heating, a T3 thermal fault, heating above 700 degrees Celsius. Over the 4-day period, the ethylene levels increased, and the rate of increase is higher than typical levels, telling us that the fault is active. And the generation of acetylene points to the severity of the fault and/or the involvement of electrical contacts. The carbon monoxide and carbon dioxide levels were elevated, and this could indicate the involvement of paper insulation in the heating. And the severity of a high temperature heating fault is higher when there's paper involvement. So we were quite nervous about this result. The oil quality results are all very good, and the furan test results on the right-hand side also very good. Paper insulation condition is excellent for a 43-year-old transformer. The degree of polymerization is 803. In a brand new transformer, the DP is 1,000, and at end of life, the paper DP approaches 200. And we believe that the mechanical strength of the paper is still as new until the DP falls to below about 600. So I reviewed the dissolved gas analysis data for the transformer, and Duval triangles are one of the ways that we can interpret the dissolved gas test data. Here we were looking at dissolved gas, the output of Duval triangle 1 for the DGA results we just looked at. For these results, the output of the triangle 1 is down here, a T3 thermal fault, heating above 700 degrees Celsius. Examples causes include large circulating currents in the tank and the core, and misalignment of contacts in an offload tap changer. The risk of failure increases if paper is involved. And for a T3 thermal fault, high temperature heating, we can also look at the data through Duval triangle 5. This triangle allows us to differentiate high temperature heating faults that are located in the oil or in the paper insulation. And for this transformer, Duval triangle 5, the output is here, which is on the border between carbonization of the paper, that burning of the paper, and T3, high temperature heating. So burning of the paper may be indicated, and this would elevate the severity of the fault. And in these circumstances, we need to closely monitor carbon monoxide, dioxide, and furan test results, because these will give us further information providing supporting evidence that burning of the paper is occurring. Carbonization of the paper can occur wherever there's paper, including on paper-covered leads, the windings, or between turns. The fault can lead to a loss of dielectric strength of the paper. This can result in a dielectric failure. We look for elevated levels of ethylene to begin with, and we will also monitor the situation of fault with by reviewing the carbon monoxide, carbon dioxide levels. So I reviewed the oil analysis data for the asset manager, and these were my recommendations. To do more frequent dissolved gas analysis, to monitor the rates of generation, to do electrical testing, to investigate the cause of gassing, to do an internal inspection when possible, to look for problems such as burn contacts on the tap changer. Also to do some other oil testing, including furan testing, to evaluate the condition of the paper or changes in the condition of the paper. So the asset manager did an internal inspection. He sent me this photo, which shows you the offload tap changer. And we can see burned contacts around here. So this is a common problem in transformers. And we can also see here some burning of this paper-covered lead. So this could be why we saw carbonization of the paper in Duval triangle 5. So the inspection also revealed significant surface pitting. And I've outlined the stages of this type of failure on the left-hand side. So you'll get a copy of this presentation. And I've seen this before, this surface pitting of contacts. Could be a manufacturing problem. But this is a good example of using dissolved gas analysis to identify a problem. We were able to intervene before a failure occurred, and I believe this transformer was repaired by Ampcontrol and Mackay. So I'll move on now to life extension, and I'll begin with the case study. So this is a mine site transformer, 2 MVA. Primary is 11. It was manufactured in 1996. So we've got dissolved gas analysis results on the left, oil quality in the middle, Furan test results on the right. We did the testing in 2020. There was some heating in the transformer in the past. The problem was fixed, and we see a very clean result here, maybe some low-level partial discharge. It's a good result. The oil quality results are not good. The moisture levels are very high. The assessment is poor according to IEC 60422. Same with the dielectric breakdown voltage, very low. And a high breakdown voltage is needed for safe operation of a transformer. The Furan test results on the right indicate significant deterioration, and the DP is less than 500. So the asset manager needs to do filtration to reduce the moisture content. This will help prevent further breakdown of the paper by water. So this is a picture from our transformer factory in Newcastle. We can see one of my colleagues building a paper winding by hand. And when the windings are constructed, the assembly goes into an oven, and this heating process reduces the water content of the paper. And when the transformer leaves the factory, the DP of the degree of polymerization of the paper will be more than 1,000. During operation, a transformer can be exposed to high levels of moisture, like the previous transformer. So this can degrade the paper. We'll see this degradation by reductions in the degree of polymerization, and DP of 200 is theoretical end of life. And there's more information about DP, end of life, increased failure risk, and mechanisms of failure in a technical presentation we recorded last year. This can be accessed by this link on the bottom of the page, and you'll get a copy of this presentation. So the picture on the right is of another transformer we've manufactured in Newcastle. You can see this one is in a later stage of the manufacturing process. So the paper insulation is brand new, and it's possible to maintain the paper in good condition for decades, like we saw with the first transformer that was manufactured in 1977. So how can this be achieved? Well, we need to control the operating temperature, since we believe that every 6 to 8 degree rise in operating temperature will double the rate of aging of the paper. So this is a very simple interpretation of complex calculations described in Monsigny's rule. And we need to also avoid moisture and oxygen ingress. So if the percentage moisture by dry weight of the paper increases to 2%, we can see paper life reduced by a factor of approximately 10. So leaks should be fixed, silica gel breathers inspected, replaced when necessary, and gaskets replaced when they need to be replaced. We recommend that you do filtration to maintain the oil in a non-damaging condition. Don't let the acid levels, or try not to let the acid levels go above 0.05. Maintain oxidation inhibitor levels at 0.3%, add more if necessary. And it's also possible to retrofill the transformer during operation with a higher quality mineral oil, a natural or a synthetic ester, to help preserve the paper insulation. A very interesting product released only last year is Nitro Bio 300X from Ninus. So it's biodegradable, and it also has very low viscosity. And this latter point is important for transfer of heat from the windings to the oil. And this enhanced cooling theoretically means lower operating temperatures, and so longer operating life of the paper insulation. And the final part of the presentation is about transformers filled with natural and synthetic esters. Two examples of ester fluids that we work with on a regular basis are MIDEL 7131 and also FR3. So MIDEL 7131 is a synthetic ester, and it was introduced to the market in the 1970s. So it's been around for a long time. FR3 is a natural ester, and it's produced from soybeans, and it was introduced to the market in the 1990s. And so, we like these fluids because they have higher fire and flash points. Typically, the mineral oil does, and this is good for fire safety. And there's not been any reported transformer fires of assets containing these K-class fluids. They're readily biodegradable, which means 60% of them, if there's a spill, 60% of the fluid will degrade within 28 days. And they're also, they have very different moisture carrying capabilities than most mineral oils do. So this means they draw water from the paper insulation, effectively drying out the paper. And degradation of the paper by water is one of the ways the life of a transformer can be reduced. We can retrofill a transformer on site, certainly above 66 kV. We recommend you work with the manufacturer of the transformer and perform an engineering assessment, so we can help with this. And after the retrofill has been done, we test the fluid in a very similar way. We take samples of the fluid, we test them in the lab. And one of the tests that we recommend after the retrofill has been completed is fire point, just to check that the procedure has been done successfully. So I'm going to focus briefly on the aging of the paper insulation in a transformer filled with synthetic ester MIDEL 7131. So regardless of fluid type, increases in water levels in the paper can increase the rate of breakdown of the paper. This breakdown of the paper by moisture is called hydrolysis. And studies conducted by CIGRE, for instance, published in 2018, indicate that significant reduction of aging can be achieved by using ester fluids. This is because they reduce the content of the water in the paper insulation. And one of the reasons for this is because they have a higher water solubility and they draw water from the paper. And the interface between the fluid and the paper insulation is dynamic as far as water movement is concerned, and also temperature affects solubility. It's a very complicated process. And on the right-hand side, I'm showing some moisture equilibrium curves for mineral oil on the top and MIDEL 7131 on the bottom. And they relate absolute water content in the oil to water content in the paper. So as the charts show, as the water content in the oil or the synthetic fluid increases, so does the water content in the paper. So let's have a look at mineral oil, 50 parts per million, like the previous transformer case study. At 60 degrees Celsius, 50 parts per million equates to about more than 3% water content in the paper by dry weight. And at these levels, we'll see elevated levels of paper breakdown, potentially. If we look at the same water content in MIDEL 7131 at 60 degrees Celsius, this looks like less than 1% water content in the paper. So in these particular circumstances, the paper insulation should be much drier in the MIDEL 7131 environment, and it follows that the rate of breakdown of the paper insulation is thus expected to be lower. So we also, our lab also tests alternative fluids. These are the tests that we can do: dissolved gas, oil quality, furan testing. Each has a particular standard that we use to interpret the numbers, the test data. Like with mineral oil, DGA, dissolved gas analysis, is one of the main tests we perform on natural and synthetic esters. The same gases are produced, but the ratios and the rates of generation can be different. And I factor this in when I do a condition assessment. And the gases that we measure come from thermal and electrical stresses, including when we see T1, T2, T3 type heating faults, partial discharge, D1, D2 discharges. We pay close attention when we see T3 thermal faults and also D2 discharges. It's also interesting that the gas generation levels and the ratios for electrical stresses, partial discharge and D1 discharges are similar in mineral oil and synthetic esters. So this helps us with the condition assessment process. And we use the valve triangle 3 to help us understand what the test results mean. So this is a recent transformer case study. It's a 25 MVA transformer filled with a natural ester. Transformer primary is 33. It was manufactured in 2012. So I've got the dissolved gas analysis and the oil quality results here to quickly review. So the dissolved gas analysis indicates high temperature heating, a T3 thermal fault, and the heating goes back all the way to 2017. The increasing ethylene levels, C2H4, are a concern. Suggests the fault is active. And this type of heating in transformers can produce carbon monoxide, dioxide, ethylene, and also acid from the fluid itself. I don't believe paper insulation degradation is occurring here. The carbon monoxide levels are not too much higher than the normal levels that we see during normal operation. And also the ratio of carbon dioxide to carbon monoxide is greater than 7. And if this decreases, then this could indicate that there's abnormal heating of paper. The water levels are within specifications for new oil, and the acid levels are elevated, 0.33. So the recommendations I gave to the asset manager recently were to continue to monitor the dissolved gas analysis regularly, 3 months I said, do thermography to try and identify any overheating of the tank, bushing connections, or bus duct, and also look at recent electrical testing to investigate the cause of the gassing. Any further increases, certainly an internal inspection will be recommended. So this is the final page. So in 2019, CIGRE published a technical brochure called Condition Assessment of Power Transformers. The publication outlines development of an asset health index system that can be used to assign a condition score to the asset. Provision is made for assets filled with mineral oil, natural and synthetic esters. Above is the summary table for a synthetic type ester. The process uses a color-coded scoring matrix. You see this on the left. It also gives us recommendations for dealing with problems. It's a pretty simple tool to use from CIGRE. I recommend that you take a look. I'll quickly show you how it works. If we pick a particular test that we do from an oil sample breakdown voltage, let's imagine your transformer primary is less than 72.5 kV. If the result that you get from your test is more than 50, you'd be given an A assessment, A, which means minimal signs of degradation. And if you get an E, so if the score from the lab is less than 30 kV from the oil sample, this means very poor condition, high likelihood of failure. Reconditioning, reclaiming, or replacing the dielectric liquid as soon as possible is recommended. So it's a very useful tool that we can use to create a condition assessment, and it will give us a clear understanding of what is happening to the transformer. So that's the presentation finished. I'll look at the questions section to see if anyone has left any questions. Certainly, if any oil analysis results indicate a problem, please send them through. My email address is below. Question: is stray gassing more prevalent in certain makes and designs of transformers? So this is low temperature heating of the oil, and certainly we do see in newer transformers of the seal type, more distribution size, we do see some more low temperature overheating, which may be a consequence of the design of the transformer. So yes. So what is the difference between periodic and continuous DGA? So periodic DGA, dissolved gas analysis, is when you take an oil sample and you send it to a lab. Continuous dissolved gas analysis, this is when the testing is done via a monitor that is attached to the transformer. There's a number of reasons why we would do SFRA on an in-service transformer if there was a short circuit event and if there was any concern, for instance, that there'd been movement of the windings. This is one of the tests that we would apply, and from the test data of the test, we would look. We would compare the testing to historical test data. Yes, there is a difference between mineral oil and synthetic ester. Recommended methodology for oil sampling to prevent contamination. So we recommend you use a 50 ml glass syringe to take the sample. And also use a glass bottle to take a 1 liter sample. So the glass should be amber colored. This will help prevent any degradation of the sample. Best not to take a sample on a windy day. We don't want to get particles into the oil sample. And also try not to do any sampling on a rainy day as well. How do you locate the points on a Duval triangle? I'll contact you separately about this, Ragab. When should we test for corrosive sulfur? Is it the same as DBDS? I'm going to talk more about corrosive sulfur in my next presentation in a couple of months. I think it's worth doing a one-off corrosive sulfur test on any transformer. If the result comes back as positive, then you can actually directly measure DBDS. Can replacing mineral oil with ester oil be used as a transformer drying process in place of lengthy filtering process? Certainly the manufacturers of the fluids believe that replacing mineral oil with a natural or a synthetic ester will actually serve as a transformer dryout. So theoretically, yes. Does Ampcontrol offer a drop-in service for samples? Yes, we do. I think they're all the questions I'll take for now, and I'll look at the rest of them and come back to you with questions separately, privately. Thank you very much for joining, and I hope the presentation was useful.